Okay. Uh, Hello. Good morning or good evening. Uh, some of you requested I um, film some videos for the homeworks, and so I'm just going to record me going over the homeworks from this semester so far. So we'll start with problem set number 1. This first question, we want to add the missing hydrogen atoms to each of the following molecules. So what we're looking for here is who is not following the octet rule and their valence electron rule. So at this point, I hope you all know that oxygen likes to have 2 bonds, carbon likes to have 4 bonds, and nitrogen likes to have 3 bonds. And so we can go around each of these molecules and make sure that everyone is happy, and add in hydrogens for those atoms that need 1 more bond. And so I'm just looking for, with a lot of these, or with all of these actually, the carbons that only have 3 bonds instead of 4. So next is a little bit more complicated. In this one, we are looking for all the implied hydrogens. This kind of structure is called a skeletal structure, where we just have those kinds of lines, and we take each of these turns or like bends in the lines as a carbon. So adding in all of the hydrogens, we know that this C would need 3 more bonds. And then we can work our way around all of the carbons here. So this has 3, it needs 1 more. Same over here. This one already has all 4, so it does not need any more. Same with these 2 here. So we'll add 1 here, 1 here. And just try to fit them in where you can. Okay. So the next one, or next question, is identifying stereochemistry of the indicated atoms here. And so for this one, we want to remember the VESPER uh, stuff that we covered in class, VESPER, which helps us determine geometry based on our electrons. So with this first oxygen, we have 2 bonds, but oxygen still needs to follow the octet rule. So there are also 2 lone pairs. We have 2 things attached, so this will be bent. And sometimes when we're talking about electronic geometry, we'll also refer to it as tetrahedral. So with this oxygen, both of those attachments are to carbons. In this one right next door, we have 1 to carbon and 1 to a proton, but we're still following the same rule where we have 2 bonds and 2 lone pairs. So this one is also bent. And when talking electronic geometry, tetrahedral. So moving down to this carbon, we have 1, 2, and then a third implied hydrogen as our 3 bonds. And this double bond is just kind of reinforcing this bond. It's not adding anything to the electron. So when we have 3 bonds like that, we have what is called trigonal planar. And if we were to look at this in the 3D, those 3 bonds would be flat, and we wouldn't see them coming into the 3D. So moving along here, we have these 2 hydrogens to add, and that makes this carbon It has 4 substituents on it, so that will be tetrahedral. Here we have the same as we saw earlier, where there's 2 carbons. One is a double bond, and then we have 1 proton. This will also be trigonal planar. Now, I've left this last one because it's a nitrogen. We have our 3 bonds here, and then we have this lone pair. Now, you might say there's 3 substituents here, so it must be trigonal planar, but we can't forget about this lone pair. And lone pairs kind of push our other substituents down, and so they make a pyramid. And this is trigonal pyramidal. And because, like the oxygen, where we have our lone pairs, this lone pair makes it electronically tetrahedral. So moving along, I kind of already touched on this with the previous question, but we just want to add in our lone pairs to this structure and make sure that everyone is following that octet rule that you should remember from Gen Chem. So part D, quinine has 5 chiral centers. Identify each with an arrow. So when we have 5 chiral centers, we're looking for 4 unique substituents. And so anything that has a double bond, we can knock out here because it won't have 4 unique substituents. So we get here, and we have an OH, we have this fused ring system, we have the nitrogen ring system, and then we also have that proton. So that is 4 unique substituents. This is a chiral center. Moving down, we have this one, which will also be a chiral center. It has the proton, the nitrogen. This attaches, you don't want to think about it as just attaching to the carbon next to it, but that it attaches to the rest of the molecule. And same this way. So then that same idea will apply for this carbon as well as this carbon. And then we have our nitrogen, which has these 3 visible carbons attached to it that are all unique, but also the lone pair. And nitrogen can be a little bit tricky when deciding if it's chiral or not. But you want to look for these kind of fused ring systems. They are basically forcing that nitrogen into a specific configuration. And because it can't move or like change that configuration, it has to have a set 3D structure, which is basically what we mean when we say something is a chiral center. Okay, so labeling identical atoms on the following 2 structures. This one is pretty straightforward. You can just pick a place to start and start numbering. We'll see if did I get that one? Yes. 9. So I won't number all of these atoms for the sake of time, but as long as you have the major gist, it's easy to tell whether you have the correct numbering between the two. And so this question with the 3D structure follows that same idea, and it just makes sure that you guys are thinking about these molecules how they are in real life, which is in 3D, instead of how they are just drawn on your homeworks. That fused ring system is probably the trickiest part of numbering this quinine structure. So the final part of question 1 on homework 1, or question 2 on homework 1? Yes, question 2 on homework 1. What disease is treated with quinine? This is one that you can use the internet to help you answer. And the answer is malaria. So we're going to repeat those steps now with a new molecule. This one is nicotine. And so we can just go around and make sure that we're drawing out all of those implied hydrogens. And then we can look at, so now we can identify all of the stereochemistry of non-hydrogen atoms. So starting with this carbon, we have 3 substituents and no lone pair, so it's trigonal planar. I'm going to go ahead and just circle all of the trigonal planar molecules in blue to save some time. And so this is 3 bonds, no lone pair. And then in gray, I'll do our tetrahedral centers, and that's 4 bonds. Okay. So now we can add in our lone pairs. It'll only be on the nitrogens. And then identify our chiral center. So you can kind of think about your wedges and dashed wedges as arrows towards your chiral center, where you have a really big arrowhead and a tail pointing straight to your chiral center. Now, this won't always be the case, but it's a good way to visually help yourself start looking for chiral centers and molecules. And we also have an unstable chiral center here. And this isn't in a fused ring. And so there can be some movement between these 4 substituents and the electron, the lone pair, the electrons. And so that's why this nitrogen is unstable, whereas the one we saw earlier in that fused ring was stable. So our next question is just drawing the enantiomer. And so an enantiomer just means the mirror image. And so with this one, it's pretty simple because we only have 1 chiral center and it was wedged. So now we'll do dash. So there you go. That's the chiral center, or the enantiomer of that chiral center. And then we will just number the identical atoms here. This one is pretty simple. moving along. Okay, so question 4. This is one that needs documents in the homework or like pictures, um, which is not easy for me to do just on the iPad. So I'm going to skip this question. But if you have questions about it, you can email me or bring it up in the exam reviews because I have a little model and it's more helpful to see this in real life. Okay, so next is drawing the 2D and 3D structures. I will just draw the 2D structures because I'm just on my iPad, but you could do the 3D structures using PubChem. So starting with riboflavin, fun fact, this is the molecule that my research with Dr. Begley is based in. So we have this ring system, and then there's nothing chiral there, but off of that we have a ribose chain that has 3 chiral centers. And so when you draw the structure, you'll see these 2 wedges and 1 dashed wedge. Each of those centers is a chiral center. So next, we'll do phenylalanine, which as we've moved on in our course, you've seen a lot more of as it is an amino acid. So we have this benzene ring to start, and then we have the acid part of our amino acid, the carboxylic acid, and then we have the ammonia or amine part of our amino acid, and this right here is our chiral center. We have the benzene off this way, the acid off this way, the amine, and then that implied hydrogen. Next is acylclovar, acylclovar, and it has a pyrimidine uh, base to the molecule. And then it has this chain. And so actually with this molecule, we don't have any chiral centers. And if we want to go through these individually, this one has 2 hydrogens, so it doesn't have 4 unique. Same with this carbon and this carbon. Then we have this carbon has a double bond, which means that it only has 3 substituents. Same with these ones that also have double bonds. And so we're only left with nitrogens, and none of them are in those fused ring systems. So we could, if we wanted to, call this one a unstable chiral center, but for our intents and purposes, this has no chiral centers. And then finally, we have dideoxythymidine. Oh, got a Y. And with this one, we have this cycle that has a heteroatom, and then another cycle with heteroatoms, a methyl group here. And then off to this side, we have an alcohol. So again, we have those arrows that are helping us point out those chiral centers. So there's 2 here. Okay. Question 6. I won't cover this one in the homework just because I'm sure each of you has different answers based on what your major is and what molecules you picked. But moving right along to homework 2, we're going to start off with a very similar question as to what we saw in homework 1, which is just adding all of the missing hydrogens. And so we know that all of our carbons need 4 bonds. So I'll just start by filling all of those in. And I apologize if my hydrogens start to look like nitrogens. I hope that with context clues, you guys can all figure out what I'm writing. I think I got all of them. So now we can look for atoms with trigonal planar geometry. So that means that we have 3 bonds, or three substituents is maybe a better term, and 0 lone pairs. Or maybe it's better to say 3 pi, or no, sorry, sigma bonds. Because what we will see is that our trigonal planar atoms often do have a pi bond. And so this one might catch you off guard. Why is this nitrogen trigonal planar? Well, it's trigonal planar because there's a resonance form of this molecule that looks like this, where we do have 3 bonds and no lone pairs. And so when you see this functional group, which you should recognize as an amide, those nitrogens will be trigonal planar. So moving on to those with trigonal pyramidal geometry, this again will have 3 bonds, but will now have 1 lone pair. And so there's actually only 1 atom in this structure, and it is this nitrogen here. It doesn't have a double bonded oxygen adjacent to it. This is a tertiary amine, not like this one, which is an amide. And then finally, we'll identify those atoms that have tetrahedral geometry, meaning they have 4 bonds. And this is going to be most of the molecule, or the carbons in our structure. Actually, yeah, the only one that isn't is our amide. So now we can identify our 10 chiral centers. If you'll remember my arrow trick, we can identify some of these very, very quickly. And so with that trick, we identify 1, 2, 3, 4, 5, 6, 7, 4, 5, 6, 7, 9 of our chiral centers, and the only one missing is our unstable nitrogen chiral center. Moving on to a question that should be pretty familiar by now, labeling the identical atoms. I'll just pick one side. Oh. And then I'll follow that same convention on the 3D version as well. So now we can identify our functional groups. I don't know why my picture is cut off here a little bit, but we're looking for alcohol, amine, ethers, bioethers, oh, bioester, bioether, and amides. So I'll do a little color coordination here. Our alcohol functional groups are going to be COH, and then amines are nitrogens. They're often written as NH, but I earlier pointed out this tertiary amine, and that is because it has 3 carbons attached to it. It's still an amine because amines are any combination of carbons or hydrogens. If you were to have an NH3, if you were to have NH like this one, we would not consider that an amine because we have to look at the whole picture. And so that is actually one of the other functional groups we've set out to identify. That's an amide, which is where you have an acyl or a carbonyl next to some kind of amine. So our final 2 functional groups, ether, that's when you have an oxygen in the middle of a carbon chain. And finally, thioether, which is where you have a sulfur in the middle of a carbon chain. And so we have another question where you would look this up. Lincomycin is an antibiotic. I don't know where my text went. Okay. So, question 2. Predict the direction of the following reactions. So for this one, we would need our pKa table, and we would look for the closest matches to these pKa's. So here we have an amide, and the pKa of an amide is 15. And on this side, we have a protonated amine, and the pKa is 10.6. With these predict the directions, you always want to point to the higher pKa because that is the stronger proton or stronger bond for the hydrogen, less likely to come off and be in this basic form. So, moving to our next one, you might think at first that this is just an alcohol, but we want to think about it in its entirety. This is a phenol, and the pKa is 10. And then over here, this is the same or similar to how I had mentioned tertiary amines. this is a tertiary alcohol with a pK of about 18. So again, we want to point to our bigger pKa. Finally, we have SH, which is thiol, with a pK of about 10.5. And then here we just have a primary protonated amine, which has a pK of about 10.6. These are close enough together that we would see them in equilibrium. Usually the rule is plus or minus about 1 to be in equilibrium versus picking a certain direction. So next, we can do one of these drawing a molecule questions. I usually like to start these off with a cyclohexane, not a benzene, but just a cyclohexane. And then each of these functional groups required, build them off of my cyclohexene. So a double bond, which is also called an alkene, I'll build off of this one. An ether, which we just talked about a few questions ago, is an oxygen in a carbon chain. And then we have an amine. And then we can add a carboxylic acid and a thiol. So we can indicate all of our chiral centers. And then I'm going to forego the pK values for now because they'll each be different for each of your molecules. Next, we can identify the acidic protons for each of the following compounds. And so in this one, what you want to do is just circle one single proton. So in this first example, our molecule is actually symmetric. So whether you circle the left or the right proton, either of those is correct, but it is going to be the proton that is attached to this oxygen. Next, we have a thiol, and so that proton will be our most acidic. With this one, again, any of these protons would be the correct answer. And now, given these protons identified, we can find the pKa's. And so for this one, we just want to look at our pKa table and find our best matches. Once we have this, we can rank the compounds in order of increasing acidity. Now, acidity and pKa have an inverse relationship, so our strongest acid is going to be our lowest number. So I'll go ahead and number these compounds out. And our lowest number is -7, so we know that's going to be our biggest. It's our lowest value, so it's our strongest acid. So next we look for our next lowest number, 4.7. And then we have 6.4, 10.5, 10.6, and 15. And so our pKa's are in decreasing order. We put them in small numbers beneath here. We can see that they are decreasing as our acid gets stronger. So now we can draw the conjugate base. Now, conjugate base is just what has happened after that proton has been lost. So with our first one, we have this original structure. If our proton is removed, these electrons have to go somewhere. They'll go back to our oxygen. And so our conjugate base has that anion on the oxygen, or a negative charge on the oxygen. So now we can go through our other structures and follow the same thought process. That's sloppy. We'll write it out. Well, I'll just say. And so those are our conjugate base structures for this. So question 5 is looking at which of the molecules are identical versus enantiomers. And Dr. Begley has said this, and I would like to also encourage you guys that really the best answer to these kinds of questions is to make models so that you can see it in the 3D. Now, if you were to do that, you would find that none of these molecules are identical to A. And one way that we can look for this is an enantiomer has two pieces basically switched from the substituents. And so if we look at A to B, we keep this CF3 the same. They are both in plane. And then our proton is also in plane, but the bromine and the methyl have flipped. So now we have a bromine here and a methyl here. So A to B, those are enantiomers. If we were to compare A to C, again, we can keep that CF3 in plane, and now we'll keep the CH3 in plane, but our proton and our bromine have been switched. So A and C are also enantiomers. Finally, we have this structure D, where CH3 is still in plane and is the same as A, and H, our proton, is also in the same position, but our bromine and our CF3 have been switched. So A to D is also enantiomers. Now, an enantiomer should all be identical. There's only one mirror image that we can take of A, and so B, C, and D should be identical. So if we go to check our work, we can look, and we have between B and C, this CF3 is the same, and we could switch the places of our bromine and our proton. So if we were to draw out that little intermediate, and then we were to switch our proton and our methyl group, you would end up at C. And a mirror image of a mirror image is the original image. I was trying to think of a way to draw that, but I don't know if I have one. So you'll have to take my word for it until you can make some models. But moving along, we are going to draw a 2D representation of this molecule. So we know that we start with a CH3 here, and that is then attached to this 6-membered ring. now we can fill in the double bonds that we see, as well as the other substituents. So we have another carbon chain here, and that attaches to another ring, 5-membered ring. Not my best 5-membered ring. But we have a methyl group off here. Oh, and oh, that's why it's not my best 5-membered ring, because it's not a 5-membered ring. Forgot this carbon. We can add our double bonds in and add our alcohol chain. And so, there you go. Next, we are doing a little bit of spot the difference between these two structures. The first one that I see is that this methyl group is no longer here. And then we can kind of just trace down the molecule, comparing the two, and we'll see that this double bond is missing in the other structure. The chirality of this center is different. And here we have these two methyl groups that here are 2 protons. So there you have the 4 differences. So question 8 is a use the internet question. And so we can draw the structure of the chess buffer after looking it up. And this is the acidic form, where our pKa is 9.49. But then when we have the basic form, we have lost that proton. And so this is our conjugate base and our acid. And then our useful buffering pH range, you can get this from the slides, is 8.6 to 10.0. Question 9 asked you to look back at the buffers in lecture 9 and use that to help identify which buffer to use at a solution of pH 7.5. And so using that table, you could identify heaps, Hess, and Tapso as helpful buffers. And the useful pH ranges are also listed with those. Oh, I'm going to run out of space if I write that big. And all of these include 7.5, which is the range that we're looking at. So then you could look up the structures of these. And I'll let you guys look up those structures for Tess and Tapso. So the final question of homework 3 is a math question. So nitric acid is a strong acid. And you should remember from Gen Chem that a strong acid means that it fully ionizes in water. And so if we're looking for our concentration of protons, we can assume that this nitric acid has fully ionized into its protons. And so our first step will be to take millimolar and convert to molar. The factor there is 1,000, so you can do 100 divided by 1,000, get 0.1 molar. We need to remember that we have this equation to help us. The pH is equal to the negative log of our concentration of protons. Because we fully ionize, we know that our concentration of protons is equal to that of the acid. So we can plug that in. And we get a pH of 1. Okay, homework 3. We're going to start with indicating the differences between progesterone and its analog. And so we can start with this ring. We see that what is attached at this part of the ring is different between the two. And so you could count that as one or two differences there. And we also have an extra carbon here. It's a methyl group on the progesterone and an ethanol group on the other. And then we can see that everything else stays the same. So now looking at the chiral centers, again, we can use that arrow trick to help us identify those chiral centers. Looking for functional groups, we have the double bonded oxygen in the middle of a carbon chain. So that is a ketone. We have a carbon-carbon double bond, which is an alkene. And then over here we have a triple bonded carbon-carbon, and that's an alkyne, which, by the way, single bond is an alkane. So all that changes is that vowel. And then finally here we have an alcohol. For finding the 3D structure, you can use PubChem to do this. And then we can move on to which of the following molecules are identical. So this touches on a organic chemistry concept that may have been new to all of you, the idea of cis and trans double bonds. So when we have a single bond, that's what's called a sigma bond. Single and sigma. I'm not sure how great the audio will pick up the difference in my speech there. When we have a double bond, we still have that sigma bond, but we now also have a pi bond. And this pi bond helps reinforce the connection between these two atoms. And now, because of that reinforcement, we can no longer spin freely around this bond. With these single bonds, we can spin freely. And so all of that free spinning means that A, B, and C are all identical. But when we come with our pi bonds, we're going to run into some problems. So with D, we can look at it as both of these are going to the left. And with E, again, they both go to the left. They don't look the same, but that's because the rotation that we see, specifically with these bonds is around a single bond. And so that can happen. And then finally with F, we have one that's going to the left and one that's going to the right. And so these D and E are what we would consider cis, meaning same, as they are both on the same side of the double bond, whereas F is a trans, like different or opposite double bond because we don't have them coming off on the same side. Next, this is our standard G, H, and I are our standard enantiomer questions. Again, I encourage the use of making models, but if you're not, you can just look at if two substituents are switched. And we see that between G and H, that B and C are changed. And then between H and I, A and D are changed onto a different color. And so here we have a very good example of G to H is a mirror image. H to I is a mirror image. When we take the mirror of my mirror, we end up with identical. So G and I are the same, and H is their enantiomer. And then these final ones are helping or trying to help show the difference between our nitrogen chiral centers. And so this big bubble is the orbital that our lone pair would be in. And this is not locked down by anything. So there's lots of free movement between all of these substituents. And because there's lots of free movement, they're the same thing. So next we are classifying the following as electrophiles or nucleophiles. And our electrophiles are electron hungry or deficient, whereas our nucleophiles have plenty of electrons and are called electron rich. And so kind of a dead giveaway for these is going to be if you're electron rich, you'll probably be negative, and you're electron deficient, you'll probably be positive. So if we were to color coordinate these, we could go through quite quickly and highlight excuse me, those that have the negative charge. And then we can go through and highlight those that have positive charge. So now we have some that are unlabeled, and we actually have some that have more labeling to be done. Now, our double bond here has no positive or negative, but we have to remember that a double bond is one sigma bond and one pi bond, and those pi electrons are available to move about. So we would call this a nucleophile. With the cyanide, it's pretty straightforward. With the proton, it's pretty straightforward. But this structure here has a resonance form that we can draw as this, that shows that not only is the oxygen nucleophilic, but that terminal carbon is also nucleophilic. We can do the same thing with this imine here, where we can use the double bond to give electrons to, oh, and I have it labeled incorrectly. Sorry, guys. We can use the electrons from the pi bond to give us this structure here. And with this structure, we have a clear negative charge. Oh, that should not be a negative charge, it should be a lone pair. and a clear electrophile. With this next one, there are no resonance structures, but with our last one, there is one resonance structure that will help give clarity to our labeling, because we will make an anion and a cation. And so our carbon will be electrophilic, but that oxygen will be nucleophilic. So resonance is really helpful, not only in determining nucleophiles and electrophiles, but we can also use it to determine the relative acidity. So with this, we'll compare the relative acidity of A and B by looking at resonance forms. So resonance forms are going to be basically the movement of electrons around the molecule. And so with this one, with A, you always want to start your resonance structures and any curly arrows, because we'll use this again with curly arrow mechanisms. Your base of your arrow will always be at some source of electrons, and it will land where you're putting those electrons. So with these electrons, I'm using them to make a pi bond here. And in doing that, this carbon would be overloaded. So we have to push some more electrons. And so we get this structure. Now with resonance forms, we always want to have our overall structure reserved. So our overall structure in this first one is -1 because we have this negative charge here. And in our resonance form, that negative charge has moved to the oxygen, but it's still there. Now, with resonance forms, we want to keep going until we've exhausted all of our options. So if we push those electrons back down into the system, again, we're going to overload this carbon by forming that pi bond here. And so those electrons could go to the right, they could go to the left, they could go out, but those aren't all feasible. We're not going to just kick those electrons out. Conservation of mass and energy, we can't just kick them out. If we go to the right, we'll just end up right back where we started. If we go to the left, we have to remember that there's 2 protons here. There's nowhere to put those electrons. And so none of these are viable options. And these are the only resonance structures. Now, looking at structure B, we can do the same thing we did with structure A, where we push those electrons up onto the oxygen. And we get an alkene here with that negatively charged oxygen. But now, when I push electrons back down, I can, oh, my pencil turned off. I can push these here, and now I can delocalize into the benzene ring. And I can keep shuffling those electrons around the benzene. Until we get eventually back to the start. And so B clearly has more resonance structures. That means that in the acidity of this question, we would be able to delocalize the resulting negative charge more evenly throughout the whole structure. Whereas with A, it is just localized to this little piece of the structure. And so given all of these resonance structures showing the more delocalization. B is our stronger acid. So now we can also use our resonance structures to identify nucleophilic sites within a molecule. So, like I said, we have to start with electrons. So we have a lone pair on this nitrogen that we can make use of, where we can form a double bond here and push those electrons solely onto that carbon. And so, like I mentioned earlier, we want to conserve our charge. And so our original molecule was neutral. And so with our resonance structures, we should also have them neutral. We have -1 and +1 for a total of 0. So we have identified some nucleophilic sites already. And I'll keep updating this structure as we find them as we continue on. So we can push these electrons down again. We'll still have a positive charge on that nitrogen and a shift of our double bonds. And again, we have one negative and one positive, so we're still overall neutral. We'll push these electrons once more. And finally, we'll delocalize up into the oxygen. Oh, good. So that gives us all of our possible resonance forms. And so anywhere that we had a negative end up, you can go ahead and mark as electron rich. The same idea can be used for identifying electrophiles as well. But remember I said that the butt of our arrow should be at an electron. We are showing the movement of electrons. And so if your first instinct is to do something like this, no, don't do that. A positive charge is not indicating presence of electrons. It's indicating the absence of them. It's saying there's an empty orbital here with no electrons in it. So we need to have our drawing start at a source of electrons. So what do we have close by that is a source of electrons but a double bond? So we can start by moving our double bond over. And now the electron that was here has gone away. We've created a new empty space. And so following the same idea as we did earlier, we'll continue to push electrons around. But when pushing electrons around to identify electrophiles, we're looking at where do we leave empty gaps, empty orbitals, when we move our electrons. And so at this point, I have a crossroads. I can go out into the chain, or I can go into the ring, and we'll want to do both. I definitely recommend that you all don't skip steps and go one step at a time, but I have been doing this for a little while. So I'm gonna do 2 arrows here and move our cation all the way over. We just have one more. Oh, I forgot my double bond. We just have one more until we reach back around to the start. And so all of those atoms that ended up with a positive charge on them will be electron deficient or electrophilic. So next we have a question looking for examples of some of the reactions that we have learned so far in class. So electrophilic, so we need something like a cation of some kind. And an alkene, we know that's a C double bond to a C. So we're doing it to an alkene. So our first, let me do, our starting material is an alkene. And we know that HBr is a strong acid. It'll be H plus and Br minus. And when we add that to our alkene, we'll get the proton on one side and the bromine on the other. With nucleophilic substitution, we'll need 2 nucleophiles. So you can start with any old nucleophile and you'll end up substituting it. So here, I just have the bromine. Bromine is nucleophilic. This O minus is nucleophilic. And so in a substitution reaction, I will just substitute those 2 things. So then we'll have Br minus. And finally, an acid-base reaction. You can really draw almost any structure you'd like. And just show the movement of a proton. If you want, you can also include, well, you probably should include the base. So now we can get into some of the mechanistic questions. So for this one, we're comparing the difference between SN1, which, if you'll remember, SN1 is S for substitution, and for nucleophile, and that 1 is unimolecular. And that means our first step will be just 1 molecule. This is often used when you have big, bulky groups, like these benzyl groups. And so our first step is unimolecular. We're going to actually ignore one of our starting materials. We're going to start with just one. And we'll see the loss of our leaving group. And with that, we end up with a carbocation. Another important part for SN1 reactions is that this cation can be stabilized in some way. So now that we've done our unimolecular first step, now we can think about our other reactant here. And we don't want to forget our little bromine. Now, like I said, curly arrows follow our electron movements. And so the electrons on this oxygen will attack this empty orbital or go to fill this empty orbital, and we will get our final product. With SN2, again, we'll have nucleophilic substitution, but this too is bimolecular. So our first step is going to use both of our starting materials. It follows the same science though, where we have this negative charge, we have lone pairs or an abundance of electrons on this oxygen, and this bromine is a nucleophile that we will substitute. And so we will attack, and in forming that bond, this carbon would be overloaded. We have to kick something off. We kick the bromine off. And so in SN2, you'll have no intermediate, and in SN1, you will have this carbocation intermediate. So moving along, we have analyzing this addition to an alkene, right? Because we have this alkene to start with, that we have added something new to both sides of our alkene. We're going to use the disconnection analysis. And so disconnection analysis starts with one of these curly arrows over the bonds that you are going to break. And now we can draw each of our species separately. So we'll have a star on both sides of our alkene. We'll have an H star and a Br star. And then if this helps you, you can visually put them close together because we know with the product where everything will end up. And then what's really important is that on our products, we don't just want to point to the products like I just did. It's important to show that you know exactly what about the products has changed. And so you want to point at exactly which of those bonds are newly formed. And so this carbon-hydrogen bond is newly formed, and this carbon-bromine bond is newly formed. So now we have our disconnection analysis. We can look at the curly arrow method of this. So we'll start with our starting alkene. And like I said earlier, this is a strong acid, so it will exist in its ionized forms. So we'll have H plus floating around. Like we said earlier as well, our double bonds are nucleophilic. So we will pick up that electrophile and we will end up with this carbocation intermediate. But remember that we also have that bromine floating around. And so it has just enough electrons to help us out here. And we get the addition to our alkene. So this next question might seem a little scary or more advanced, but it's following the same thing that we just covered of SN1 reaction, or well, nucleophilic substitutions and addition to alkene, kind of described in or molded into one reaction. And so something that's really helpful when you have a complex reaction like this is to start by numbering your atoms so that you can follow them through your reaction. And so with this one, I am going to label everything, but I'm going to use this 3A and 7A for when I have branching. And so we know that our phosphate group will come off all as one piece. And then we want to look at where our double bonds are. So we know that there's a double bond between 2 and 3 and between 6 and 7. So 6 and 7 we might change, but if we go about this numbering again, we can keep that double bond between 2 and 3. And so the first thing I'm going to do is I'm going to twist up our starting material to look more like our product. So we want to already take on kind of this loosely cyclic shape. I'm not going to draw out all the phosphates, I'll just abbreviate them like this. And so what is our first step in SN1? We have a unimolecular step that starts with the loss of our leaving group. Oh, I forgot all my double bonds. So we get this structure. And as we just saw with addition to an alkene, we have an electrophile right close by. We can add to our alkene. Now this part is the more advanced part of this question. We would now have a base that can deprotonate here so that we can form the double bond that we see in our final product. So that's the curly arrows behind limonene synthase. Moving to homework 4. Our first set of questions is going to ask us about identifying aromatic, anti-aromatic, or neither. And so when doing these kinds of questions, we want to count the number of pi electrons. Now, we have a couple sources of pi electrons. They can be from pi bonds, which is like your double and triple bonds, and they can be in lone pairs. Once you have your number of pi electrons, you can use this equation. Where this whole piece, what you're setting the equation equal to, is what you count from your structure. So we'll start here. We have one double bond, two double bond. Each of those double bonds is made up of 2 electrons. So we have 4 pi electrons. We plug that into our equation here, and we solve for n. Now, in determining aromatic, anti-aromatic, or neither, aromatic is when n is equal to a whole number, and anti-aromatic is when n is equal to a half number. But how do we know when something is neither? In order to be aromatic, we have to have what is called a conjugated system. This basically means that all of our pi electrons can talk to each other some way. One analogy that I've heard to explain this is like a railway, that all your pi electrons can communicate and travel across your molecule together. And so with this first molecule, we do have that. Every atom has some kind of pi electrons. So we are a conjugated system, and we get a number that is n equals 1/2. So this is anti-aromatic. Next, we can move on to our next structure. We have 4 pi electrons coming from bonds, and then our nitrogen has a lone pair. So 4n plus 2 equals 6. When we solve that, we get 1, which is a whole number. And again, each of these atoms in the ring has some kind of pi electron. So we have a conjugated system. So this is aromatic. Next, we have this benzene. We have 6 pi electrons, so we know that n will equal 1. And again, each of our atoms has pi electrons, and so it is a conjugated system. This one is also aromatic. I'll start this one by looking at the conjugated system. And we can see that along the outside, all of our atoms have pi electrons. And so we do have a conjugated system, thinking about the outside of these rings as one big ring. So now we can count our electrons, and we have 2, 4, 6, 8, 10. And we plug that into our, we have 12. When we plug that into our equation, we get 4n equals 10. And we get a half number. So this one is anti-aromatic. With this one, we have all of them having pi electrons, so we have a conjugated system. And counting our electrons, we have 2, 4, 6, 8, 10, 12, and then this lone pair, signified by the anion on the carbon, gets us to 14. We have a whole number, so we are aromatic. With this one, we have eventually a half number, so this one is anti. Here we have, we'll get a whole number, so this one is aromatic. And then this one I'll take my time with because we have not talked about cations yet. Like I said, positive charges or cations are an empty orbital where electrons could be. And so in the railway kind of analog, you can think about it as a tunnel that they can pass through. So this does participate in our conjugated system. It just doesn't add any electrons to our count. So with this one, our equation is 4n plus 2 equals 2. N equals 0, which is a whole number. And so this system is aromatic. Now, with these final 3, you'll see that the only thing changing between these 3 is what's going on with this carbon. So in this first one, we don't have any charge. That means that there are 2 protons here, 2 implied protons. That means that all of the electrons available to this carbon are locked up into sigma bonds. We have no pi bonds there, which means not a conjugated system, and therefore neither. This next one, though, we now have a positive charge, which means that we have that empty orbital for the electrons to be in. So we do have a conjugated system. And we have 6 electrons, which would make this aromatic. And our final one, we have an anion instead of a cation. And that will add electrons to our count. So we have these 2 for the lone pair, bringing us to 8 and making the total system anti-aromatic. Now, this might be confusing, the negative and the lone pair. They are redundant. The lone pair usually probably wouldn't be drawn in on a carbon. We would just indicate its presence using the negative charge. So, moving along, we have drawing all of the resonance structures of indole to predict the products of the following reaction. So, we'll start with moving our electrons around. We have a lone pair on the nitrogen. I'll start with the blue. And we can start pushing our electrons around. We'll have a positive charge on our nitrogen now, and a negative charge here. And so we'll continue to push these around. We can now push them around through the entirety of the ring. And we want to remember to keep our charges constant. And so as we work our way through all of these resonance structures, we will quickly find ourselves back to the starting point. And now we can basically neutralize again. Well, we'll make our way around the ring again. So we can go, oh, my pencil's not working. We can push these electrons here. And this will bring us to the starting point. Now, from this starting point, we could have also taken those electrons the other way and gotten a whole new set of resonance structures. I won't draw them all out, just for the sake of time. But we end up with a negative charge on every single carbon in this molecule, which means that our electrophile can add to any of those positions. So you could have drawn out, or should have drawn out 1, 2, 3, 4, 5, 6, 7, 8 products. So moving forward, we're looking at the disconnection analysis of the following reaction. We start by disconnecting what is broken, and then we can draw our star species. And we will forego this cation. It will become a star species. And then we can shift these around so that that's too many. There we go. Shift these around so that our stars are rearranged closer to their reaction products. And then we go to our products, and we have to indicate that new bond formed, and then conservation of charge. We started here with a +1 charge. Here we have that +1 charge. So now we can look at the experimental mechanism of this reaction. So we'll start with our starting material drawn out here. We have that tertiary amine, and then we have our 2 double bonds and all of those methyl groups. And so we want to start with electrons. We have that lone pair on the nitrogen, which can move all the way about the ring to where we then get an or a nucleophilic double bond that can attack our cation. So that gives us this intermediate. Where we have this double bond here, here, and let's add those methyls back in. So we have our original +1 charge, and now because of that nitrogen, we have another +1 charge. But to neutralize it, the pKa of this proton is going to be pretty high now. So a base can come in and take that proton, shifting the electrons back around until we get our product. So the next question was looking at a 3D structure. For that, you could use PubChem, and you would number those corresponding atoms. Next is good practice for the final, definitely, is being able to identify the following reactions. And so I'll kind of break down how I approach these questions. So the first thing is looking at what changed between our starting material and our product. And what we can see here is that where this bromine once was, there is now a new functional group. And we know that bromine is a nucleophile. We can see that this is also a nucleophile. And we haven't just added, what we've done is we've substituted. So This is nucleophilic substitution. In our next one, we can see that where there used to be two protons, there's now only one proton. Where there used to be no protons, there's now one proton. And so if we were to color code these, we could say that it's something like this. And then all that's changing is the location of a proton. That is an acid-base reaction. Finally here, we can see on our starting material, we have this alkene that is no longer an alkene because instead we have added a bromine and a proton. So we have addition to an alkene. We also know that HBr exists as its ions, and that H plus is electrophilic. So we'll go ahead and add in electrophilic addition to an alkene. Next, we have question 6. We're going to create a molecule again with 15 carbons, at least one chiral center, and a variety of functional groups. So as I've said, I love to start these ones with cyclohexanes and then add each of those functional groups off of my original cyclohexane. So we'll start with an ether, which is just that oxygen in a carbon chain. Then we have a ketone, which is a double bonded oxygen off of a carbon chain. Alkene, I hope we know at this point, is a C double bond C. An alkene, or sorry, a carboxylic acid is quite similar to a ketone, but you will have this OH. And so I don't want you guys to be thinking of this as a ketone. You have to think, or this as a alcohol or hydroxy. We think about our functional groups in their entirety. So that is a carboxylic acid. And then finally we have a thiol. And then just to double check, I have at least one chiral center. I actually have 4, 5. And then 15 carbons, I have 6 in my ring, 7, 8, 9, 10, 11, 12, 13, 14, 15. So now we want to look at the products of the following reactions using what we have here. And so what we have here is an acid. And we know that an acid can do addition to an alkene. And so I'm just going to quickly copy paste my structure here. And then clean up some of these labels. And so we will have this alkene here. We can do an addition to it. And we end up with bromine on one side and the proton on the other. Now, with this, we also have a base, which we had our carboxylic acid. We can do acid-base chemistry with that. And if we take our structure again, and let me clean up those annotations and put back my double bond. This proton can go to our base. And so we will have a deprotonated carboxylic acid or carbonate. And we'll have our negative charge there. And finally, we have CH3, or this methyl iodine, which can also be drawn as and so we can do a nucleophilic in a sense, a nucleophilic substitution with our thiol group here. Oh, let me just copy paste it. Where instead of this proton, we'll add on that methyl. And so that is reactivity using our compound that we made and some familiar reactants. Okay, moving on to homework set number 5. First, we're looking for redox reactions. And so redox reactions are the gain or the loss of electrons. And so with our first one, this should be something we recognize because here we have a nucleophile that is trading places. So this is nucleophilic. I'll just label it as SN. It could be 1 or 2. So that's not a redox. But here we can see that it might be hard to tell just because the notation is different for these two carbons. But we're going to lose these 2 protons to form 2 more pi bonds. So that is actually going to be a 4-electron oxidation. So the mnemonic device for this is oil rig. Oxidation is losing electrons, and reduction is gaining. And so we had to lose these protons, but also had to lose electrons in that as well. And so how exactly can we determine that? Well, there's a bookkeeping method that we can use for oxidation and reduction reactions. So we'll start with drawing out our starting material. And we know that in order to get to our ending material, we're going to have to lose those 4 protons. So if we draw first the loss of those protons, we end up with this structure. Now, we can't do bonds between 2 negative charges. We can make bonds between a negative and a positive charge, though. And so if we were to get rid of some of these electrons, we would be able to set ourselves up to make some bonds. So I took them all for nitrogen, but you can really take whatever smattering of them you would like. And then we can use these electrons to make those double bonds, and that is how we get to our product. And so we had to lose 4 electrons Oh, that's so we have a 4-electron oxidation. So next we have labeling some functional groups on the structure of this nicotinamide. And so some of these are words you might not have heard before, and so you might have had to look them up, but some should be familiar. So I'll start with those that should be familiar to you all. The amides should be familiar because it's an NH next to a double bonded oxygen. Then we have alcohols, which is just that OH group. And we have ethers, which are oxygens in the middle of carbon chains. And then now we have those ones that you might not have heard of before. But as we are coming into the final stretch of class, adenine you should recognize as a DNA base. And then we have that phosphate diester. And finally, the pyridine. So next we could look at the 3D structure of NAD in PyMol, or well, PubChem. PyMol is another software, but you guys won't ever need to use that. And determine trigonal planar or trigonal pyramidal. This can also be done just with your understanding of molecular geometry and electronic geometry. And all of these will be planar. Moving along, we have drawing out all of the resonance forms of this piece of NAD. So you'll see this part here is what we have drawn here. And so we'll draw out the resonance forms to determine which of these are electrophilic sites. And so this one can be pretty easy. We can keep it relatively contained inside the ring. And so our first structure we have this cation, can have this cation, and one last one. And so highlighting our electrophilic sites are those that ended up with the positive charge. So next we are looking at which molecule is oxidized. So which molecule loses electrons and which is reduced. So it gains electrons. A good example of oxidation and reduction to just kind of memorize, or you'll see it often enough that you should recognize it, is an alcohol to an aldehyde is an oxidation. And so we would say that our alcohol here is oxidized, which means that our other molecule has to be the one that is reduced. So we can break this down to look at how many electrons are transferred. So if we're looking at just the first half, we know that we'll have to lose 2 protons, start moving in the right direction. And then in order for those 2 things to come together, we'll have to turn one of them into a cation. And so we know it's a 2 electron. Now we can use curly arrows to put these things together, where we start with our alcohol, and we have NAD that can be used to take up, well, this is NAD plus, that can be used to take up the electrons that we will generate in this oxidation. So we'll have a base come in and deprotonate. And that will push electrons all the way around until we get to our aldehyde now and our reduced NADH. And with our conservation of charge, we now know that our base will be positively charged. So next we can move on to NMR. And so with this, we can break down into our number of proton groups. And so with our ring here, we have a symmetry, plane of symmetry. So these 2 that are across from each other, we'll call that group A. We have this one here that is across from each other, we'll call that group C. We have our alcohol proton, we'll call that proton group C. And then we have another plane of symmetry here, which means that these 2 terminal methyl groups are the same or chemically identical. We'll call that D. And then this little linker we can call E and F. So now moving into splitting data, well, we'll start with signal integration. So signal integration is telling us the number of protons per group. And so I'll do that in this blue. So this will be 1, B has 2, A has 2, E has 2, F has just 1, and D has 3 on both sides, so D is 6. Splitting patterns, this is where we look at our neighboring protons. So B has no neighbors this way, but 1 neighbor this way, and our rule for neighbors is n plus 1. So we would expect a doublet. A, we have the same thing, no neighbors here. We have a neighbor in B, so we would have a doublet. CH2 and E, we have no neighbors this way, but we have 1 neighbor in F. That's also a doublet. With D, in both cases, our only neighbor is the oxygen, so that is a singlet. And then with F, we have no neighbors with either of those carbonyls, but we do have 2 neighbors with E, and so n plus 1, we would expect to see a triplet. For chemical shift data, you'll use the table that will be given, but now we can assign all of our signals. And so C is easily assigned to us already. We only have 1 signal that is, it's hard to see here, but a triplet and only has a signal integration of 1, so that must be F. Then we have our two aromatic doublets. Those usually have a chemical shift of about 7, and so that helps set these doublets worth 2H apart from this doublet worth 2H. And so we can label these as A and B. We know that this long or tall singlet has to be D because that's our only 6H group. And with process of elimination, as well as the data we have corresponding to it, we know that this is signal E. And so we'll follow that same pattern with our next NMR. So we have the plane of symmetry across our benzene ring. So we have group A, group B, group C, D, E, and F. Looking at our signal integration, we have 3, 2, 2, 2, 2, 3. Then we can look at our splitting patterns. Singlet, doublet, doublet, singlet. E here has 3 neighbors. We would expect a quartet. F has 2 neighbors, so we would expect a triplet. And then we can use our chemical shift data from the table to help us. So we only have 1 singlet that's worth 2 integration, so this must be signal D. We can use the same thought process for labeling this peak here as signal C. Here we have a 2H quartet. That must be E. We only have 1 3H triplet, which must be F. And finally, we have our A and B. I prefer to start with the rings, and so we'll start with A and B, C, D, E. This will have no protons, neither will this one, and F. Going in with our integration, C is worth 3, A and B are each worth 2, D is worth 1, E is worth 3, F is worth 3. Then we can look at our neighbors. C has no neighbors, we would expect a singlet. A and B both have 1 neighbor, we would expect a doublet. F has no neighbors, we would expect a singlet. D has 3 neighbors, so we would expect a quartet. And E has 1 neighbor, so we would expect a doublet. And now we can go through and label. So we should have 2 3H singlets. So we would use our our chemical shift table to help us identify these signals. And with that help, we can identify this as C. And, oh, sorry, I've got those flipped there. We can identify this as C and this as F. We only have 1 signal that has 3 protons and doublet splitting, so we know that this is E. We only have 1 that is a quartet, 1 single proton, and then again we have our aromatics. So now we can look at using the NMR data to assign when we have multiple options for a product. So I'm going to go through and start labeling these. So for this one, we have all of these methyl groups that are exactly identical. So it's actually only 1 signal here, and it'll be worth 9 protons and be 1 singlet. They all have the same neighbor that has no protons. For our next one, we do have these two, which are identical. So it's 6 protons. They do have a neighbor. This is signal C. It has 1 proton. And so one neighbor, we would expect B to be a doublet. C has 3 neighbors here, 3 neighbors here, 2 neighbors here. At that point, we just call it a multiplet. And finally, D has 2 and just sees its neighbor next door. So it's a doublet. Next, we have this chain where we have, we'll call this signal E, which has 3 protons. It sees 2 neighbors, so we would expect a triplet. Then we have F, which is 2 protons. It sees 3 to the left, 2 to the right. So you would expect a sextuplet in the splitting. G is also 2 protons and sees 2 neighbors on either side. So we would expect a quintet. And then we have H, which only sees, well, it's 2 protons that only sees its 2 neighbors. So it will be a triplet. So now we have all of these signals assigned. We'll look for the NMRs that match what we have drawn out. And then also we will have all of our hydroxy groups. So compound 4 will be the easiest to assign because it should be just one giant signal. And lo and behold, we have one giant signal. So this is compound 4, and this is signal A. Next, we can look for compound 5. We would expect to see 3 signals there. And we do have an NMR with 3 signals. We have compound 5 here. This would be signal B, signal C, and signal D. And finally, we have process of elimination, identified spectrum 6, or compound 6 to spectrum 2. But to confirm, we can go through and label all of our signals as well. So we know that this 3H must be E. We have our 2H triplet, which will be H, G, and S. We can continue this thought process to identify which product is the major reaction product when we have multiple options for product reactions or for products coming from a reaction. And so we'll start by breaking down our product signals. So with 8, we would expect to have five signals. And with product 9, we would expect to have only 4 signals. So that can already be a giveaway because we have 1, 2, 3, 4, 5 signals in our NMR. So already we should be thinking that our major product is probably 8. But we can go through and confirm that. A should have integration of 3, B should have 2, C should have 1, D should have 3, and E should have 3. Then looking at our neighbors, A has 2 neighbors in signal B, and so we would expect it to be a triplet. B has 3 neighbors in signal A, and 1 neighbor in signal C, so we would expect that to be a quintet. C has 2 neighbors in B, which means it should have a triplet. And then both D and E are isolated and should be singlets. So we can go through and label our signals now. We know that there are only two options for these 3H singlets, and so that must be D and E. Then we only have one single signal that has one proton in it, so this must be C, this must be B, and this must be A, just based off integration. But looking at our splitting patterns, as well as our chemical shifts, it confirms everything we've laid out here. So now, moving on to homeworks 6 and 7 and their combined state. Our first question is looking at disconnection analysis. And so we want to start by breaking those bonds that will be broken with our squiggly lines. And so for that, we will draw out these protons explicitly to show that only one of them is getting broken off. We can then do our asterisks or star species. And so everywhere that we had broken a bond, we will turn into a star. And then you can rearrange if you find it helpful. I'm going to forego that for now, but now we can point out exactly which bonds are new in our products. Using this, we can then try and figure out our curly arrow mechanism based on what we found from our disconnection analysis. So we know that the carbons and carbonyl groups are slightly electrophilic, and we have this lone pair on the nitrogen that can act as our nucleophile. So if we attack here, we can push the electrons up onto the oxygen, making this tetrahedral intermediate. And now we will have what is called the collapse of the tetrahedral intermediate, forcing the loss of our leaving group. This leaving group can then pluck off one of those protons, and that gets us to our neutral ending point. Well, not really neutral, because this negative is conserved. So, moving to the question on orlistat. Our first step is identifying the functional groups and chiral centers. So first we have this double bonded oxygen next to an oxygen embedded into the carbon chain, and that is called an ester. Just above that, we have a double bonded oxygen next to a nitrogen, an amide. Here we have another ester. And now we can look for our chiral centers. And so we have our arrow pointing to this one and these ones. Next, we can look at how a basic buffer can affect the reactivity of our orlistat. And so looking at our reactivity, these esters are more reactive to bases. And so in the presence of a base, we could have the opening of this ring. And that would definitely function or remove all of the function. And so to just hone in on this little part of the orlistat, we have this ester and any old base. Now, these acyl groups are electrophilic at their carbon sites, and our bases serve as nucleophiles. And so we can see attack of the base onto that acyl group and the formation of a tetrahedral intermediate. Then when we collapse that tetrahedral intermediate, we end up opening the ring. And this is where we lose activity. So moving to the next reaction, we have a known product and we know what kind of reaction. So now we have to determine what those starting materials were. So we know with an aldol condensation that it's starting with two ketones and ending with this ketone and the loss of water. We know that loss of water happens because it's a condensation. And so this double bond is where we would have lost the water, and that shows us where our two starting materials came from. So if we draw those out, we end up with the alcohol or the oxygen that ended up in our water. And the proton that ended up in our water. And so we have our two ketones, or in this case, I've drawn that wrong. Sorry, guys. Yes, our two ketones. That would be our starting material for this aldol condensation. Question 4 is very similar. We know with a Claisen reaction, though, that we need to start with two esters. So we're looking for, we have this carbon between our carbonyls, and that indicates to us where our oxygen used to be. So we can snip there. And we needed two esters. So we have the carbonyl part. We have to add on what else is needed to make it an ester. And then we can add in the rest of our molecule. And we get our two starting materials. So with this question, it's about helping to visualize where R1 ends up in 19 or 20. And so instead of drawing out the R groups, I am just going to rename 5, 6, 7, and 8 as R1, 2, 3, and 4. So R5 will be R1, and then we'll have R2 as R7. We ultimately lose R4 as R8, and then R6 is R3. So whichever of these that you picked as R1, as long as you see that it is the same in both, you have gotten the answer correct. So now, looking at disconnection analysis of this Claisen reaction, we know that we have to lose this proton and that we will be losing this part of our ester. And so we end up with these star species, and this new bond is formed, as well as this. And so now we can look at the curly arrow mechanism for Claisen reactions. We need to use this base first, and so we have R1, and R1 will deprotonate adjacent to our ester. The resulting anion is a great nucleophile that can attack the electrophilic center of our other methyl ester carbonyl. And with that, we will form a tetrahedral intermediate where everything is attached briefly. Oh, not be double bond. And with the collapse, oh, I forgot an oxygen. With the collapse of that tetrahedral, we'll pick off one of those oxygens. And that will give us our final product, but not all of our final products, because our leaving group will be negatively charged, and we need to restore our catalytic base that we formed in this first step here, and we can do that here. So we have our big product and our smaller product. Now, I don't say major and minor because we would make these in the same ratio, but big in relative size. So this next question was looking at if the following compounds are soluble or insoluble in water, and a soluble molecule is a polar one. That's ones that have lone pairs and charge. And so I'll just go through and highlight those that have charge and lone pairs. And so those that don't have your relatively insoluble in water. So next we are doing a disconnection analysis on this molecule here. And so we can see that this bond is broken and we're going to lose one of those protons. And then we can draw out our asterisks. Oh. And then we can indicate on our products which of those new bonds are formed. And here we can see that it is an acyl group that is basically just trading. And so that's an acyl substitution. So I'm going to forego the bonus question for now. Moving to question 8, we can do a disconnection analysis on this lysine modification. And so we know that we'll lose one of these protons and we will lose the fluorine. And so we can draw out our star species. And then indicate which of these bonds are newly formed on our products. We will do a similar thing with question 9, looking at cysteine modification, where we are going to break this disulfide bond. And this homework actually has an error in it. There should be another S right here. And so this is the new bond formed. And we can also draw out all of our star species. Because this molecule is the same, I'm just going to put it in a bracket times 2. And so we have added this whole functional group onto the protein. So now looking at a protein, we are going to identify, these are called quaternary structures. They're like motifs in the structure. Or no, this is tertiary. Sorry, guys. And so alpha helix is going to be this stuff in red. These yellow are your beta sheets. And then finally, these green areas are your disordered loops. The next part of this question is asking you to draw an amino acid sequence. And so for this, we would need our table of amino acid structures to help us fill in our R groups. But before we even do that, we can draw out the backbone of a peptide sequence. They will always start with this amine terminus. And then you have 2 carbons and another amine. 2 carbons. Oh, that's 3 carbons. And another amine. And we have 4 here. So I will put my carboxy groups in to help me keep track of how many amino acids I have drawn. And then our last one will end in the carboxylic acid. And so you'll notice that we have amine, carbon, carbonyl, repeated. Amine, carbon, carbonyl. Amine, carbon, carbonyl. Amine, carbon, carbonyl. And so these carbons that I've identified here, that is where your R groups come off that are making those specific amino acids unique. Their structure's unique. So you'll take this 1-letter code and you'll identify the structure that corresponds on your table and you'll add in your R groups. And so first, C is glutamic acid. And then we have Y, which is tyrosine. And then we have L, which is leucine. And then we have Q, which is glutamine. And so you'll just draw in all of the R groups as they are written on the table. So next we have a callback to our oxidation and reduction reactions. In this one we are oxidizing NADH and reducing this CoA molecule here. And then we can do disconnection analysis. We're going to break this double bond and we're going to lose a proton here. And then we can draw out all of our star species. And then we can identify which bonds are new on our product. And now we can move to our experimental mechanism. And so this is the structure of NADH. And NADH is one of those cofactors / molecules that you should know and recognize. So all of our curly arrows start with electrons. We're going to start with this lone pair here. It's going to kick electrons up until we're not going to lose H plus, which is a proton. Instead, we're going to lose H minus, which is a hydrogen. And so this proton and its electrons are going to come over here and kick that double bond there. And so the first intermediate that we'll get out of this will be this structure here, and our NADH has become NAD plus. Now this loose proton can add to our anion and we get to our final. So coenzyme A is nature's acyl carrier cofactor. That's an important statement to remember. can get this line. I will not be drawing the structure of CoA, but know that there are some important functional groups and chiral centers to identify with this reaction. I'm going to skip right to part D. A through C, you can check the posted key. And if you have questions, feel free to reach out. But disconnection analysis, we'll see that this S-CoA is broken off, and we lose this as a decarboxylation. So when we draw out our asterisk species, we get all of these. And then pointing to those newly formed bonds, we get these. So how exactly does this happen? Looking at our curly arrows, again, we always want to start from electrons. So we have this lone pair here, and we can, first step, decarboxylate. So now we have an anion on this carbon, and that can attack our carbonyl here, forming a tetrahedral intermediate. And then with the collapse of that, we will lose the other S-CoA and get to our final products. Okay, last homework assignment here is homework 8. So our first step is going to be drawing a reaction coordinate diagram. Now, remember that these are related to energy and enzymes, because enzymes take what would be a difficult reaction, and instead of having one big step, they use many small steps. And so our reaction coordinate should look something like this, where we have our starting material, and it takes some energy to get to our intermediate, and then some energy to get past it, and we get to our product. And so here we have the starting material, this other dip is our intermediate, and our final plateau is our product, which the y-axis for this is delta G, or the energy. So now, looking into these reactions, we have a PLP-dependent enzyme that does the racemization of 4 to 5. So proposing a mechanism to this follows pretty much exactly the PLP mechanism that is in the slides. And so PLP, we draw that out. Is attached to our enzyme and has this imine. I mean I-M-I-N-E, not A-M-I-N-E. We have oxygen and then an organic phosphate group. And so our first part of this is going to be imine transamination, where we'll basically trade this amine for an imine bound to number 4. And that will look something like this. Following that transamination, we can do the actual modifying of our amino acid here. And that is done by deprotonation. So we will lose this proton. I shouldn't have started with the charge there. And because we now no longer have our 4 unique substituents, we lose chirality here. And so now the enzyme can put the proton back on in a stereospecific way that changes the chirality of this center. And the final step here is just going to be another transamination that puts the PLP back onto the enzyme. So the PLP will look like this again, and our product will be released as the other isomer, or the other enantiomer. Next, we have a reaction catalyzed by a thiamine-dependent enzyme. And so for this one, we want to know the structure of thiamine. And really the main takeaway with these is what purpose the PLP and what purpose the cofactors serve and what reactions they most notably participate in. And so just drawing out the structure of the thiamine here. We are going to eventually see decarboxylation. So in PLP, we saw transamination reactions for racemization. In this, we will see some acyl chemistry that ultimately gives us decarboxylation. And so this nucleophile of the thiamine can attack the acyl group here. And we will get a tetrahedral intermediate. And for the sake of time, I'll just write it as TPP for thiamine pyrophosphate. And in the collapse of this tetrahedral, Instead, what we see is a tautomerization where this proton ends up over there. And now we can see decarboxylation. That can then be protonated, and eventually we'll see the loss of the TPP, getting us back to 7. Now we can identify each of these following reactions for question 4. And so this is about recognizing your starting materials and your products. And so with our first one, what we see here is this nitrogen is nucleophilic, and we have an acyl group here, and this will basically trade spots with this other nucleophile. So we have an example of acyl substitution. Next, we have this aromatic system here, and we have an electrophile. So we have electrophilic aromatic substitution. Now, in comparing this starting material to this one, we can see that this has basically just been doubled. And the key functional group here is an ester. And what reaction do we know that uses 2 esters and a base, but our azane condensation? So next is building up your toolkit with stuff that we have learned so far. So acids, there's a lot of examples that you can use for this. You can do something like HCl or HBr. You can also do some kind of carboxylic acid. For our bases, we know some simple ones like NaOH, but you can also do some more organic ones like this deprotonated alcohol. Electrophiles, we know, are those electron-hungry things. So you can do something like this, or our very simple one is H+. Our nucleophile, often things with negative charges or lone pairs. And so for this, you can do really anything. There's a lot of options here. Oxidizing agents and reducing agents, we have NAD plus and NADH, which have very similar structures. With this amide, and then NADH is going to have a neutral nitrogen, but 2 protons up top here. And don't forget that R group. with question 6, it required looking back at sorry, required looking back at some of the lecture slides. So you have specifically looking at reactions 2, 4, 7, and 9, Claisen condensations, substitution in acyl groups, nucleophilic substitution, and additions to alkenes. So the lecture and slide number and examples, I'll just refer you guys to the uploaded key. And then looking at part C, looking at which have a carb anion intermediate, those are ones that have a negative carbon. We can identify acid-base chemistry, elimination reactions, aldol reactions, and Claisen reactions. Whereas carbocations, those with a positive charge, we can identify our addition to alkenes, our electrophilic aromatic substitutions, our nucleophilic substitutions, but only SN1, and our eliminations, but only E1. And I should mention here that the carb anion is only E1CB. This was part of one of the major questions on prelim 2, was the difference between this carbanion intermediate and carbocation intermediate in the two kinds of elimination reactions. And that brings me to the end of all of the homeworks. Good luck on the final. If you have any questions, you all should have my email. But that's all for me.